My name's Artash.
And my name's Arushi.
Thanks for having us here at the Science Center meeting today. We are a maker family, and we've been making projects for the last 5-6 years. And we're really interested in space and science. And today we're going to share a bit about one of our recent projects. There are many satellites and orbiters and inside in the solar system and a bit beyond. And they take images, videos, and they get lots of data that we receive on Earth and so how do we get that data on Earth? So the main way to get data from these satellites on Earth is through the DSN, the Deep Space Network. The Deep Space Network is an array of 3 giant radio dishes, basically radio antennas, spread around 3 places on Earth. So on Canberra, Australia, Madrid in Spain, and United States in Goldstone. So all of these 3 places are around 120 degrees away from each other, so that we can communicate to any satellite anywhere at any time. So yeah, here's just a little image showing the different areas that the DSN covers. So it's communicated to over 33 spacecrafts, and it operates 24/7, 365, or in some cases 366. So the DSN is used in almost all of the missions that go beyond Earth. So not only the United States, but also the European Space Agency, India, and Japan. Now, the DSN is really interesting and amazing invention because otherwise, without the DSN, we wouldn't be able to do all the communication between the missions. The farthest probe that the DSN is communicating with right now is the Voyagers. And so, since it's so interesting, we wanted to remodel a bit how it works ourselves. So, a couple of weeks ago, there was a rocket making workshop at the Carr Astronomical Observatory by Tony Harvarton, and lots of people learned how to make model rockets. So, we wanted to get a bit more out of our model rockets, and we wanted to actually get telemetry data from our rockets, just like the DSN gets data from its satellites. So recently we participated in an event with Kitsko Jeunesse, and they also gave us a box of microbits, so 10 little chips that have a couple sensors and pins, and they also have an accelerometer and a compass. So we thought we could hook up a microbit to our rocket to collect acceleration on X, Y, and Z axis and compass readings. And so basically there was 2 microbits, one of them on the rocket, one of them connected to our laptop, and the one on the and basically they communicated through radio at a frequency of around 2.41 gigahertz. So yeah. Here's an image, the microbit in the rocket, and we taped the microbit to our laptop to get the data from the rocket.
So we wanted to find out what was the range that the microbits could communicate to each other. So at the Carr Observatory, we did an experiment and found out that it could communicate the most distance when the receiver was very high.
So yeah, we had to do a bit of coding to get all of this working. So we used one of the microbit programs, a JavaScript editor, pretty simple, and we created this code that basically set a radio frequency, 228. It's not really radio. There's different channels because microbits can transmit between a certain radio frequency, and within that radio frequency, they have 256 channels that you could use. So here on the start, I'm setting the transmitting power to the maximum at 7, so we can get the largest distance. I'm setting the radio channel. And here I'm just getting the acceleration data, combining together in CSV format, because CSV format's a good way because computers can read it really easily. So we were able to get pretty good data. Not the full flight though, because the microbits didn't have that big range and the rockets flew pretty high. So we were able to get most of the launch of the rockets and part of the descent. So here's a graph of the Z accelerometer readings at the open house a couple weeks ago. And so it's measuring right now in gravitational forces. And on the x-axis is the time. So that's just the raw data. Then we wanted to analyze it further, of course, to get more out of the data. So we calculated the velocity too. So we used the formula final velocity is equal to u, the initial velocity, plus at, acceleration multiplied by time. So you can see at the beginning the yellow line is the final velocity, and the blue line is just the acceleration upon the z-axis. So at the beginning, until like 6.88 seconds, you can see that the line's pretty straight. So it's basically on the launch pad before getting launched. Then on the yellow line, you can see it's jerking up. And on the blue line, you can see it's like kind of making like a little rectangle up. That's the launch time. So it goes up, the acceleration gets higher, and then it reaches the top, basically, where the parachute pops out of the rocket to slow down its descent, and the acceleration is slowly decreasing as the rocket goes down. So we also attached a camera on board the rocket to just like get a video of the rocket, and I'm just gonna play it.
Five, 4, 3, 2, 1, fire!
Yeah, you can see the pond at the Astronomical observatory. It went pretty close to the pond, but luckily it didn't go into the pond. I mean, we were able to get the camera back. So to improve our little project here, we wanted to get a bit more range. Like if we're gonna launch rockets higher with more powerful motors, you know, the little motor that goes in the back of the rocket to power it up. We want, like, you know how the DSN has many different radio antennas, like on each side it has 4. So we wanted to create like a mesh of microbits so that we could point them in different directions. So at the beginning, there's one pointing just towards the launch pad, so we could get when it's launching. Then one pointed all the way up, so maybe we'll get a bit more distance on the top when it goes even higher. And another thing we could do is like, maybe like if we're gonna put 200 meters, a microbit can maybe do 100 meters on a good range, like no big jerks in the data. So we could put a drone at 100 meters. So the rocket would transmit to the drone. The drone would take the signal, reinforce it, and send it back to the microbits on the base. So just here's live, you know, on the DSN website, they provide live data. Not actually the data, but they tell you which radio antennas are transmitting at what time, and whether they're transmitting to the satellite or the satellite transmitting back to them. So I'm just going to show you the live data. it's not actually showing on the screen. But right now in Madrid, there's one of the radio antennas, 54 that's transmitting, and 3 others. Sadly, I can't actually get them on the screen. So since we wanted to just make a little model of how the when the DSN communicates to different satellites using the website that you get live data from. So
Yeah. So we took a kind of a box, kind of, and then we attached a puzzle to it, and to show where the DSN is communicating.
basically, we wanted to put a big space background to represent where is the DSN communicating. So we took an old solar system puzzle that we got like 6-7 years ago, and we pasted it as a background for our project. So you know how there's 12 different radio antennas. Well, we couldn't actually get all of the 12, but we took 9 of the radio dishes, and we programmed a small Wi-Fi Arduino to kind of like a little Wi-Fi protocol to the website to know when is the dish transmitting at what time. And there was 9 LEDs on the board here. So 3 LEDs represented dishes from Spain, 3 from Australia, and 3 from the United States. When the dishes are communicating with the satellite, the lights start flashing.
So yeah, this is the old solar system puzzle. Because of the limitations of the chip we are using, we could only get 9. So it's just connecting to the internet, and once it connects to the internet, it's able to log into the DSN network, and is able to get some of those ports basically. So the whole idea is we wanted, the DSN doesn't make it available using an app. So what we tried to do is we did a coding with using the XML files basically, and whenever the XML file picks up a data, like it's blinking in the USA right now, and as Artash said, in the Madrid basically, the Spain one. So the idea for us is to be able to get the live data from the different DSNs, and we actually did an outreach at the Future World Conference, and we showed it to Babak Fardowsi. I mean, he's the guy, the Mohawk guy, the guy who actually launched the flight director for the Mars Curiosity. And we were very happy when he was able to immediately point out and say, it misses out 3 dishes because we only were able to program 9 of them. So this was a small project where we ended up linking up what's happening live in different countries, and bringing it back as an educational kind of a device for schools and other outreach.
Thanks.
Okay, questions?
Next time you do your rocket flying, would you consider doing more than one flight to gather more data?
Well, at the Astronomical Observatory, we were only able to do 1 flight with the microbit because we didn't have much time to launch rockets. But just a couple days ago, we went to the Cambridge Rocket Club field. So they have a field near Guelph where they launch rockets with up to G engines, huge rockets, like this high. And we launched our rocket 4 or 5 times, and we were able to get data, 5 different graphs of data. which we are now analyzing. And yeah.
Hi. First of all, again, extremely impressive. And my understanding, I could be wrong. It's been a while since I've read into this, but I think that the way that radio telescopes work a lot of the time is that they operate on a basis called radio interferometry. Does that sound familiar? Have you heard of
No.
that term? No? Do you know exactly how these satellites communicate with each other over that long period or that long distance?
How satellites communicate between themselves, or
Yes.
how? Well, satellites themselves have dishes.
Yes.
So within the Earth's orbit, it's not that large of a distance between the
No.
satellites. So even when they're small dishes, they're able to still communicate to each other.
In the radio
and-
frequency. Yeah.
Actually, this is not the radio interferometry actually in this case, because it's simply communicating. As soon as the satellite passes overhead over the 120-degree angle of the particular, the site basically, it's able to get, it's able to link up basically, upward link and a downward link. And that's when it's able to transmit the data.
Oh, really?
So I'm not sure about, but yeah, these dishes are also used for scientific experiments, basically finding the time it takes for the data to come back, and that they use it for basically trying to find the speed of the velocity of the satellites.
Right.
And they used it during the Cassini-Saturn because they found out when the Cassini was passing through the rings and above the rings, so they were trying to see how much the radio waves changed when they passed through the rings and without the rings. And that's why they were able to analyze what the rings were made of.
Oh,
So that
I
was
see.
the whole idea.
Okay. Well, that's a very useful application to find how fast the satellites are traveling, because if you're detecting when these satellites pass over a certain point, the only lag you're dealing with is the time for the signal from the satellite to reach your detector. And considering the speed of light, that's extremely fast, right?
Correct.
Wow, okay.
Thank you.
Thanks.